because we're so first time class. It's like 40. Yeah, and one of the, I'm gonna say it's one of the like. Someone called the dead animal.
Okay. Well, I caught a pretty good bug on Friday night, and I took a 12-pound diet nobody can take. So I don't know if we're going to make it a full 50 minutes. The thing that I decided, and I sent y'all the email out on this, posted an announcement on Blackboard that instead of lab today, we're going to do some notes. We've already got 9 labs in. I'm pretty happy with that. The other one, we're going to do chromatography. By not doing the lab, it's going to allow us to cover that chapter. So that's instead of trying to cram things in the next week and a half, I would rather spend the time and work problems in class and be able to do that. So today, what we're going to do is finish up chapter 14. Then we'll move into the pre-lab or in the lab time. So let's start at 1:30. I know I'm going to need a break after 2 classes to get some food in. And we'll go from 1:30 to 3:30. So we'll be done today. It's going to be the schedule this afternoon. If you haven't downloaded notes for chapter 19, chapter 15, chapter 18, go ahead and get those. Chapter 15 is very, very short, and we'll go over that pretty quickly. And my goal would be to start chapter 18, which is spectroscopy. I thought I'd already turned my phone. Okay, so that's our plan of events, and let's see how that's going to work out. So we're talking about electrochemical cells. Still in chapter 14. And we said we had a couple of different types of cells, and we looked at the flow of the electron currents. We identified what the anode and the cathode were. We said that a reaction is galvanic, meant that it was spontaneous. The other option was that it's electrolytic. Electrolytic has to be driven away from equilibria, and that means you have to have an external energy source to accomplish that. So also in electrochemical cells, there are 2 different classifications, reversible and irreversible. Now, reversible cell, a simple way to think of it is recharge. Okay, if you change the direction of current flow, the redox reaction goes in the opposite direction. So that's a battery, like a lead acid battery in your car, that you take energy out of it, and then when you're running your car, you can charge it back up. It's an example of the battery that's in your cell phone or your computer or your lithium ion or your nickel cadmium, whatever that battery may be. You take energy out of it away, and you put it back in the charger, you drive it away from equilibrium and charge it back up. Now, not all batteries work like that. Like if you take an alkaline battery, so a 9-volt battery, the little square ones, or if you take the 1.5-volt AAA, AA, C, or D cells, those batteries are not rechargeable for the most part. There are some that are rechargeable electrochemistries that work in it. The traditional Duracell, Everready, whatever, those are one-way reactions. So if you hook one of those up and you try to recharge it, it's an irreversible cell. A different half reaction occurs than the chemistry that occurs in the forward direction. So some reactions are reversible. Sometimes when you switch the electricity around, things goes in different ways. So one of the things we want to be able to do, and I talked about these in the video, is to be able to describe without drawing a full picture out of electrochemical cell of what's going on. So to do this, we do this shorthand representation. And in this, we describe a cell in terms of a couple of different dashes. So we've got solid dashes here and here, and these represent a phase boundary. So that means you have a difference between a solid and a liquid. Okay. The double dashes represent a salt bridge. So it's your separation of your anode and cathode. So you got those 2 things pulled apart. And here's the key thing: you always put the anode on the left. That means the cathode's going to be on the right. If it's an inactive species, like a counterion that serves no purpose in the electrochemical reaction other than charge balance. We don't describe it. And the cell as written is galvanic. And the reason I know it's galvanic is it occurs spontaneously. So this is the silver tree reaction that we've done. I could make it the copper tree by making the silver, instead of being the cathode, make it the anode, put it on the other side. And now the copper is going to be plated out at the cathode. But by looking at that, I know that's electrolytic force, still the anode's on the left. And I don't have to specify what the voltage of the battery is. I just know it has to be enough to drive it forward. Now, one of the questions you probably should have is, how do I know which one's going to be the anode and cathode? That's exactly where we're headed to. So if we look at this cell, we want to write it shorthand notation for it. So I've got just some things I should be able to pick up for this. I've got the anode on the left. I've got the cathode on the right. All right, so I know what the anode and the cathode are. I've got just some things I could pick up on. I've got a cadmium solid, and I've got cadmium in solution, so this cadmium 2+. So probably the event that's occurring at the anode is the oxidation of the cadmium. And then on the other side, I've got the silver electrode and the silver cation that's in solution. So I've got those things that are available for the reaction. So if I'm going to write out this redox reaction and to write out the shorthand of it, so I'm going to have my phase boundary representing the difference between the cadmium solid and the cadmium 2+. Now here it doesn't tell me the concentration, but I would need to specify what the molarity is, because the cell potential is dependent on the molarity. Right? The nitrate doesn't matter because it's a counterion and it's not electroactive at all. So then I need a phase boundary, and I go to my other side and I have to have my silver cation, and whatever its concentration is, represent that a phase boundary in the silver electrode. So that's a shorthand representation of what's going on in that cell. Okay, so if I look at how current flows, and I talked about this in the videos, but just quickly want to highlight that. 3 different ways that currents can flow in a cell. Number 1, it can be carried by the electrical conductor, so within the electrodes, the wires, and in that is the flow of electrons. Metal-metal bonds, state electrons, the outer valence electrons are free to move around with ease. That's the reason they have low conduction. In solution, it's carried by the anions and cations within the salt bridge. And one of the places we have to exchange the electricity is at the surfaces between the electrodes where oxidation and induction occurs, and that occurs with ionic conduction. So that's where the redox reactions are actually occurring at. So you've got the cations and anions exchanging for electrons that are flowing in or out, produce your different species. So if you want to kind of take a breakdown of that, you've got the flow of electrons occurring inside of the conductors. Right? You've got oxidation occurring at 1, where the electrons are being given up and they're flowing away from this thing. So you got a flow of direction of electrons in this direction. And the other side, you've got the electrons being accepted. As the electrons are being accepted, the silver cation actually adds onto this surface. So if I measure the weight of that silver electrode after a period of time, it got heavier because it gains some atoms. Okay, so it's electroplated those silver atoms on the surface. So you've got the conduction in the solution at the electrodes, current carried in the wire, and then among the solution itself, the salt bridge, whatever the counterions are, the cations and the anions, they move around to give charge neutrality inside of the solution. Okay, so I want to know which one would describe this cell. Just as a hint, you got to figure out who's been oxidized and who's being reduced. Which one goes on the left? Which one goes on the right? got 6 answers. Again, I was here. That's the group. Last 2. Okay. Okay, most of you think that it's choice A.
So none of us are right?
None of us are right. Okay, so let's think of the why. You've got species in solution, go into a species in solution. There's no phase bound between those two. Okay, so those two are separated simply by a comma. Here you've got iron 2 plus going to iron 3 plus, so it's losing an electron off. So it is oxidation. On the other side you have the fluorine gas going to the fluorine anion. But again, there's no solid here. The electrodes could be anything. Here they're platinum on one side and carbon put on the other. They could both be carbon, they could both be platinum. The two things, half cells, are separated from one another, but on the other side you have the reduction of the fluorine gas into the fluorine anion. So the key thing on this is that there's no phase differences. I guess that would be the hint I want you to look at. Okay, so what's the difference between C and D that you see? Because they look pretty similar. Okay, so the fluorine's on the wrong side of the salt bridge on this one. And I switched the two of these around. Usually you put the element that's going to be oxidized being first. And when they're all in solution like that, I would accept them if you put them in either order. So if you would have put the iron 2 plus in front of the 3 plus, this is the correct way that you should put them. Okay, so we leave them marked. All right, so again, this isn't something new that you'll see, but your challenge is going to be when you get a problem in it, whether it be on the final exam, that's the way it's going to give you the problems, or if it's on the nested test, you have to be able to convert this into whatever redox reactions are actually happening. So you got to be able to figure that out. So next topic is looking at electrode potentials. So key thing about electrode potentials is that you can't measure them individually. We know the potential difference is the difference in the electrochemical potential measured between two electrodes, and it's an indication of the status of equilibrium. And we talked about what happened with the silver tree, the one that we looked at earlier. If both the cation and the anions are both cations, in this case the metal, the copper and the silver, they both start out at 20 millimolar. The potential difference in the cell, as we measured, is the difference between E cathode and E anode. So E of cell equals E cathode less E anode. Now the cathode potential, if I could measure it individually, is 0.6984 volts. The anode potential is 0.2867 volts, and the difference in the two is the 4.12 that we showed on the top of that slide. Okay. So what happens at equilibrium is that these two things become equal to each other, and E of cell equals 0. So just what the heck am I talking about? A couple of confused looks. I'm going to run back a few slides. There it is. Okay, so here's the system we started. Here's that original 4.12 volts starting off at 0.2 or 0.02 and 0.02. And as this thing approaches equilibrium, it's going to go all the way down to 0 in the system. Okay, so what's happening is when it gets to 0 is that both of these things, the electropotentials, are not 0, it's that they're just equal to each other. So there's not all the potential energy gone out of a cell, a half cell, when it reaches, the system reaches equilibrium. It means the two things are offsetting one another. The thing about electrochemistry is you can't have one without the other. You can't have an acid without a base. In the same sense, you can't have oxidation occurring without reduction. So without something taking the electrons, there has to be something giving the electrons. So we never can measure these half cells alone. It always has to be a coupled system. It's always relative to another electrode. So here was the silver tree that we looked at. And over time, what happened is this system reaches equilibria. And the way that it reaches equilibria is that the concentration of the copper increased. So the copper plated came out of into the solution, made the copper 2 plus cation. Because it was at 0.02, it increased to full 50%. Right? What happened to the silver? It was 0.02, but then it went all the way down to 2.7 times 10 to the minus 9. So what we see is that the two half reactions are equal to each other at 0.29 volts. Therefore, E of cell is 0 in this thing. That's what's happening in a electrode or an E cell that reaches equilibrium. So something starts off with a high potential and it goes down to reach equilibrium when E of cell equals 0. How long is that going to take? That depends on a lot of factors. It depends on what's the rate of current flow. It depends on the size of the electrodes. Things like diffusion start to come into play, and how quick those redox reactions can occur. So that's a complicated set of parameters that describe that. If you take a graduate course in analytical chemistry, so there's a course that you take actually called electrochemistry, and you start to learn about all these factors that come into play in like battery design. Even if you're measuring using these as sensors, what are the limitations that you have? What are the limiting factors that tell you the potential or the current that you can get out of? All right, so we said we need to compare all these to something. What we use as our reference electrode is a She, standard hydrogen electrode. So we abbreviate that as a She. We know if we want to make a reference electrode, so a reference electrode is going to be something that has a known potential. And we're going to use that to compare everything else to. We want something that's easy to construct. We want it to work both ways as both a cathode or the anode. And I'd like for anybody to be able to make the thing and get the same results. Okay, so reproducible. And She is easy to create and to meet those requirements, and it's a worldwide reference standard that we use. It has a disadvantage, and that disadvantage is that it's a gas electrode. So you constantly have to have a flow of gas going into it. Typically, the surface that you use for electron exchange is platinum. So it doesn't take part in the electrochemical reaction, therefore it's never consumed. So you can have a very, very thin sheet of platinum and reuse this for an eternity if you choose. You have hydrogen gas bubbling in at a pressure of 1 atmosphere. You've got a solution of acid with a proton concentration, has an activity of 1. So the capital A here represents activity, not molar concentration. So this is kind of one of the things we really haven't talked about activities. We talked about it way back in that chapter 7. But electrochemical cells are dependent on activity, not molar concentration. So activity becomes the active term. Most of the time, we're going to just substitute activity for molar concentration. We know how to deal with that if we have to. But you're bubbling this hydrogen gas across this electrode. Some of it gets reduced or oxidized depending on what's occurring in the system. You hook this up to whatever other system that you're going to measure. In this case, I'm hooking it up to the silver cation with a silver electrode and an activity of 1 molar. And I measure a potential, and that potential is the potential for the silver cation electrode at 1 molar, because the value for the She electrode is what we default to the value of 0. So we said E of cell was E cathode plus E anode. If we say this is the cathode and the anode's 0, so E of cell equals E cathode. Okay, so we've got a way that we can assign values to everything else. So the reaction that occurs, it's a reversible reaction. It's hydrogen plus picks up 2 electrons to produce hydrogen gas. This is written as a reduction, but it can go in the opposite direction, the oxidation. So the previous reaction we looked at Here it was working as oxidation. Okay, so it's on the left-hand side, so it was going in the reverse direction as oxidation in this case. It can go either way, so depending on what half cell that's coupled to, it can serve as the anode or the cathode. We just set it as a definition of 0 at all temperatures. So whenever we measure a cell potential, it's a half cell of interest working as the cathode, and the standard hydrogen electrode working as the anode. Now the key thing on this is that it's always going to be written as reduction for the thing that we're interested in looking at. So whatever our component of interest is, we're looking at it as a reduction event. Now, not everything is going to be electropositive with respect to a sheet. Okay, sometimes it's we're going to have these things where even as reduction, the potential is going to be negative part. So when you look at the table of standard electropotentials, you're going to see things that go up to a positive 3.5 volts, things that go to 0, and then the sheet is going to be in their middle at 0, and things that are going to be negative with respect to that. So just keep in mind, if something were occurring and has a negative potential, that potential is not spontaneous. Okay, so it's going to be spontaneous if you let that reaction coupled with a sheet occur spontaneously. The one that's more electropositive is the one that's going to be reduced. So the She electrode would be reduced. So we've defined standard electropotentials, SPEs, of a half reaction of interest, and we do it when all of the products and reactants in that system are at unity, are at 1 molar in terms of an activity. So if we look for the reduction of silver, we'll go look at it on the next page, but here's the half cell, or the cell that represents that in shorthand notation. You have a She electrode on one side. On the other side, you have silver there at 1 molar. So you've got your 1 molar activity of silver. The net reaction that's occurring is that the silver is being reduced. Okay, two silver cations pick up 2 electrons, produce the silver solid, and there's 2 electrons involved in the hydrogen exchange, so you have to have the 2 silvers reacting with 1 hydrogen. Now this cell proceeds spontaneously, it's galvanic, and the way that I know that is because if I hook that up and run it, there's a positive cell potential. If it were being negative, it'd be electrolyte that can be driven in that system. Okay, so this is a way that I can measure the backgrounds. So this one proceeds spontaneously. And if I look at one with cadmium 2 plus, and I look at its standard electropotential, cadmium 2 plus 2 electrons. Okay, what happens with it, if I set it up with a She, is that now I have a negative potential. So the spontaneous flow of the electrons is actually in this direction. Okay, so that means that this is working as the anode, and this is working as the cathode in that system. It's going in the opposite direction.
Dr. Smith?
Yes?
I'm just curious, this might be way off base, but is this kind of how they determine that cadmium most commonly has a 2 plus charge?
No, it's unrelated to that. That has to do with the valence electron shells, okay, and where the electrons fill the orbitals out. So its charge is the charge of something is independent of what its electropotential is going to be. Okay. And we'll see that with when we look at the reduction of iron 2 plus and iron 3 plus. The potentials are not related to their charges of the cathode. Do you have questions?
Don't batteries require, or electronic devices require constant current or voltage, I guess? I'm not sure the right terminology. It seems like the voltage is dropping over time.
Okay, and that's typically true, and that's when the way electronic devices work. Most of the things that require in your let's say if it's your computer, it stacks a series of cells to give you a voltage. So whether it's 14 volts, 12 volts, whatever that may be. Typically, the computer requires about 75% of that voltage to run, and only when it drops below 75%, then will the computer not function anymore. So if you have like your car battery, for example, common car batteries, lead acid batteries are 12 volts. Okay, there are 6 cells stacked together in a lead acid battery. And you can turn your car on and the voltage be at 10 volts and your car still start. It may start a little slower, but once it gets below a threshold, you turn the ignition on, nothing happens. It's probably down to less than 7 volts at that point. There's automatic tolerance built in, so you can deal with a low battery as a battery is discharging, but it has to get 80% discharge before the device is going to work. That's probably similar to a tolerance is what you would see. Okay, so there's a built-in factor for that. Now, the way that some systems work with that is they have what's called a voltage regulator, and they take that voltage and they automatically step it down. So they take a 12-volt battery and you run it in the voltage regulator and get 6 volts out, and all the car's electronics would be running on 6 volts. So as long as there was more than 6 volts coming to that, the car doesn't know the difference. Because the voltage regulator job is to put a constant output out of it. Okay? We talk about some of that circuitry a little bit more in next semester. Okay, so here are some of the things that are need to know about standard electrode potentials. The more positive the standard electrode potential, the more powerful the electron acceptor, or the more powerful an oxidizing agent is. All right, and the arrows on the side tell you exactly what you need to see. Now, I'm going to give you tables similar to this on the exam, but they're not going to have these nice little arrows in there. So somewhere you need to understand what's going on here with these arrows, what it's saying. So the more positive, the more likely it is it's going to be reduced. Okay, so most positive standard electrode potential is species that is reduced. Right, that's the way it's going to occur. The one that's going to be you're going to have one being reduced. That's going to be reduction. It's going to be the other one. Obviously, has to be oxidation. So that's what tells us who's going to be serving as the cathode and the anode in a cell. Okay, the one that's most positive is going to be the one that's going to be serving as the cathode. The one that's the most negative is going to be serving as the anode. Now, I could hook fluorine to a permanganate reaction. Both of them are positive. Okay? And if I look at the difference out of those, I can get 1.3 volts out of it. It's the difference in E cathode less E anode. So it still could be a functional cell, but it wouldn't be the best cell. Okay? So what I tend to do is a couple of things that have the biggest difference in the system. Okay, so if I wanted to get a lot of something out of it, I couple it with, today, this is the most powerful energy storage system that we use, lithium ions. Okay, we're going from something like fluorine, so you've got a battery that's giving you almost 6 volts with a single cell. Stack 6 of those together and you got a 36 volt battery. Very strong energy source. Now, this wouldn't be ideal to use for a long-term storage because you got a gas, and fluorine gas is a very corrosive gas. So, but you could mix it with something else, probably another metal electrode, and still get, in the difference of these, almost 4 volts out of it. It'd be a good system to use. And there's a lot of different ways that that you can use lithium-ion technology. I saw in the, I guess after we talked about it in class on Monday. It's the last time we met, Monday, right? Musk, Elon Musk, the guy that's Tesla, he had did they've been having a problem in Australia with they're trying to use more solar power and more wind energy, but their problem is they can't store it. And they're having these huge blackouts across the entire country that have been ongoing for 3 or 4 years. And he told the government that he could solve the problem for them, and they went in and he did it 3 months ahead of the schedule. They produced a lithium-ion battery plant. They're taking the solar energy and the wind energy, and they're trapping it in these huge lithium-ion battery tanks, and then they dispense it out at night. And it looks to be a complete solution for the rolling blackouts that have been having. So it's a new use of technology that we didn't even know that we could do 10 years ago, and solving problems. I mean, that's been one of the biggest problems that we have with electricity is how do we store it for when we need it. There are a number of big devices that, I mean, we have peak times which we consume electricity in the heat of the day. In the summer, it's at 3 to 6. We draw twice as much energy in our residential use at those times than we do the rest of the day. So if you could figure out how to store the energy up in a giant battery, the problem is the batteries had to be so big they weren't practical. So there are kinetic energy devices. You put this huge piece of metal on bearings, you get it spinning around, stores inertial energy, things like that they use. When you have extra energy, you get it spinning, and when you get the energy out of it, you reverse the circuitry, and it becomes an alternator or generator, and it produces electricity out of it. There's one of those, if you go north of Tishomingo, towards Mill Creek, there's a big building. That's what's inside of one of those things. It's one of the first ones I know that's been in Oklahoma. But we've had a problem in this area with these times when the power surges, gets high or low. Okay, keep in mind that just depending on the flow of current, things can be different. So here's an example of what's happening with a Shia electrode hooked to a silver and silver in solution. All right, and we've got another one that has the Shia electrode, but now instead of having the silver in solution, and instead of being 1 mole of silver, now I've got a saturated solution of silver chloride. So this is the redox reaction coupled to a solubility. The solubility is going to limit how much silver can go in solution. So that's going to limit the cell potential that can be generated here. The one on the left is 0.79 volts. The one on the right is 0.22 volts. So you got to make sure that you're talking about exactly the same system. When you look at a standard electrode potential, make sure that all those components that you see in that standard electrode potential are actually available in here. The silver electrode here is, but the silver that's present in the form of silver chloride, it only becomes electroactive when it dissolves, so it's coupled to a KST. So just make sure that everything is equal in these guys. All right, so if I want to calculate an E of cell for this reaction, what I need to do is find out who's being oxidized or reduced, go to the table and find out what their potentials are. So I think these are the two tables that I'm giving you for the test. I'll go ahead and get those posted so you can use those to work problems with if you decide to. The thing I'll tell you is that some of the problems in the back of the book, you have to use the standard electrode potentials that are listed in the tables in the back of the book. And the ones in the tables in the back of the book are not nearly simplified. There's 10 pages of standard electrode potentials. Okay, you just need to take a look at those. But I'm going to give you this combination of. Okay, so first thing I have to do is figure out who's being oxidized or reduced. We've already done the permanganate as one of our examples that we've done. But the simplest thing to see is the one that changes the least. And the iron here gets converted from iron 2 plus to iron 3 plus. Okay, so to do that by gaining or losing electrons. Okay, so it loses electrons off. So it loses 1 electron. So this tells me that this is my oxidation that's occurring. So this is going to be the one that's on the left. Right? So this is the anode. And the other one is going to be, the one that's going to be reduction is going to be the cathode. As long as you figure out what one of them is, what's being oxidized or one's going to be reduced, the other one has to be the other. Okay, so it doesn't matter which one you solve. So what I'm going to do is take the one that's given for me. I need to find those components, so I make sure I've got everything that's there. I've got the permanganate. I've got the 8 protons. Okay, I don't know how many electrons necessarily, but there's 5 electrons involved with that. Then I find the products, so the manganese 2 plus and the 4 waters. So everything's there that I need in that one. So E of cell is simply E cathode plus E anode. I look up E cathode, it's a positive 1.570, less E anode. And I find E anode, so E anode is the iron, and this is the important thing. Even though it's listed in mine, it's the oxidation of Fe2 plus, picking up an electron, losing an electron to iron 3 plus. Yeah, this is what's occurring in mine. Everything that's in the tables is always as reduction. So what that means is I need to switch it around to reduction, just reverse it. So that's a reaction I need to look for as a reduction. Okay, so there it is. Okay, iron 3 plus plus an electron yields iron 2 plus, and it's a positive 117 volts. Okay, so now I know the value for the iron 3 plus value. Write it in whatever the sign is. Sorry. Set this in color. So positive 0.771, and all this is in volts. So I've got a positive minus a positive, so part of that's going to cancel out. It's around 0.8 volts. A little bit less than that. And this would be the cell potential if everything is at 1 molar. Okay, so the knot, let me interpret our, be clear you understand this. This is E naught of cell. And what the knot represents is standard conditions. So whenever you see the knot, that represents everything's at 1 molar. Okay? All right, so let's look at some key things we need to know about standard electrode potentials. One was, I've already mentioned this, we're really looking at activity, not concentration. So we need to keep that in mind. The standard electrode potential is defined when KQ is at 1. So if everything's at 1 molar, or unity in terms of activity, those ratios, regardless of whether it's going to be a KQ of 1. And this is a measure of the driving force for each half reaction. So characteristics, this is a test question somewhere in this list below, I promise you. So the standard electrode potential is a relative quantity to a cell that has the She as the anode. So E of cell equals E of cathode less 0 because She is 0. So it's E of cell equals E cathode when it comes down. We always list standard electrode potentials as reduction. It tells us what the driving force is towards equilibrium in a system. It's independent of the number of moles of products and reactants. Let me go back and reinforce what I mean on that one. So on this guy, we didn't take this number, even though this was written for one mole of it. Because it was 5 moles, we didn't put times 5 here. Because it took 5 of these guys to balance out the number of electrons. We didn't multiply it by 5. So it's independent of the number of moles of the substance being oxidized with these. So don't do that. Okay, so if it's positive, it's spontaneous with respect to a She. If it's negative, it means that it's electrolytic with respect to a She. It is temperature dependent, and typically we run these at 25 degrees. If you go back and look at these tables, almost always we specify a temperature that we run them at. That's one of the problems that we have with some batteries. Some batteries lose their potential more readily than others when it gets really cold outside. Okay, so Lead acid batteries are some of the worst, in that as they drop down to minus 20, minus 30 degree temperatures, they lose their cell potentials, drop a lot. So to the point sometimes they're not enough to start a vehicle. And you have a couple of things that when it gets cold, it makes it harder outside. One of the things is that the lubricants in your motors, as it gets really cold, those start to thicken up. The viscosity gets higher, and it's harder to get the crankshaft to start coming over as it's going through this basically sludge initially. So how do they overcome this? What's a way that they can do, especially you hear it with diesel motors, because diesel motors use a higher viscosity oil than gasoline motors. So you know what you do?
These coils on.
Okay, what do they do with the coils?
Just heats it up.
Okay, yeah, an engine heater. So whenever you see, a lot of times you'll see a rancher or something that's, you'll see them on TV, looks like there's an extension cord hanging out in front of their car. And literally it's a plug-in. They pull the car up to the, wherever it is, whether it's inside or outside, and they plug it in, and there's a small set of heaters that run in there to keep the engine oil warm and the compartment warm. So you have enough energy to start your vehicle. All right. Okay. So the thing that's going to be the most effective electron acceptor, to the thing that's going to be reduced, is going to be the thing that has the most positive potential. We talked about this. We're just going to reiterate that. So that's going to be the best oxidizing agent. That's going to be the thing that picks up the electrons. The most effective reducing agent is going to be the thing that has the most negative potential associated. So what we need to be able to do is to be able to look at half reactions and figure out who's going to be oxidized, who's going to be reduced, using standard electrode potentials. And it's really simple. The one that's most positive is going to be the one that's going to be reduced. The one that's most negative is going to be the one that's going to be oxidized. Okay, so let's look at this one. I want to calculate the cell potential and determine whether the reaction is going to be spontaneous or non-spontaneous, as written below. All right, so let's try to figure this out. So here's my reaction that occurs. Copper is being oxidized into copper 2+. So if I look at what's happening with the copper is going to copper 2+ by losing 2 electrons. What's happening to the magnesium is the magnesium is going from magnesium 2+ to magnesium solid, and it's picking up 2 electrons. Okay, so the one that's being reduced, okay, is the magnesium, so it's working as the cathode. All right, so if I look at its potential, right, E of cell for this thing out. It's always E cathode, less E anode. And if I look at its cell potential, okay, the one that's going to be reduced is first. So the magnesium 2+ plus 2 electrons yields a magnesium solid. It has a potential of negative 2.37 minus that of the what's happening there at the anode. So even though what's occurring in its reaction is the copper solid is yielding copper 2+ plus 2 electrons, it's actually oxidation that's occurring. In the table, I'm only going to find it as reduction. So it's going to be spun around. So realize that I'm looking for it to be spun around. That's the way I see it. Its value is a positive 0.34 volts. So when I put those two things together, I got a negative minus a minus, so a negative 2.71 volts, if I can add some small numbers correctly. So now we've calculated the E naught of the cell. Okay, so this equals the standard electrode potential. So is this going to be spontaneous or non-spontaneous? It's negative. So that's what tells you if it's spontaneous or not. Is it a positive value or a negative value? This is an electrolytic cell. It's having to be driven to be here. Okay? All right. Seems simple enough. This one's yours. This is terminology. Couple more. Last one. Last chance. Okay. Okay. Well, it's either A, B, C, or D. So nobody said B. Okay. So, well, I know it's not A because the electrical potentials are going in the wrong direction. Okay. So for it to be able to oxidize, silver, the potentials would have to be reversed. So it can't be A. Nickel will only dissolve in oxidizing agents. It's going to dissolve best. Well, we just don't know anything about its solubility. So that's just a distractor that's thrown in there. So nickel 2 plus is a good reducing agent. You know, it simply can work as a reducing agent, causing something else to be, but it's barely below zero. So anything below zero is good with respect to She. It just depends on what it's coupled to. It's usually something that's going to be a good reducing agent is going to be something that's got a value of less than 2, -2. That's what we consider to be good. But we know that silver can oxidize the nickel 2 plus because that's the reaction that's going to occur with this one. This one's going to be the reduction. This one's going to be the oxidation that's going to occur because of the potentials. Yeah, that's terminology you need to get used to. All right. So in terms of an analytical tool, this is where all the other stuff was Gen Chem background. First half of the chapter. Now we're wanting to put this to work, and we're going to utilize the effective concentrations because we want to be able to look at cell potentials and find out what the concentration effects are. Sorry, my wife did. My alarm didn't go off. You were supposed to tell me when it happens. Okay, we'll continue to start this afternoon, 1:30.
Dr. Smith, I have a quick question about the lab.
Yeah.
When I put my data in, I